Hello everyone. Thank you for sticking around for this last session of the day. I'm very happy to see you here for this talk that is my favorite topic on intuitive conception. So our symposium is entitled The Persistence and Transformation of Intuitive Conceptions, Cognitive, Instructional, and Socio-Cultural Perspectives. Sorry, just a second. So my name is Katarina Gvozdic, and I will be sharing this symposium with Andrew Shtulman, Christian Thurn, and Florence Hebel. So we have a slightly different order than the one that was announced in the program, but I hope no one's disappointed with that. So I will start with this talk on... Or not. Oops. I will start with this talk on the typicality effects of arithmetic reasoning among adults and teachers. So I'll just set this up. And so I work here as a lecturer at the Department of Psychology and Educational Science in the IDEA Lab. And this study is part of our work on how a meaning of mathematical concepts is constructed, where we focus on analogical processes and the role of prior knowledge. And this is part of the work on intuitive conceptions. So, to start off, since I'm opening the symposium, maybe I'll just give a brief definition of what do we mean when we talk about intuitive conceptions. So there are numerous terms that are used in the literature, starting from intuitive theories over misconceptions to naive analogies, which all kind of describe this knowledge that is acquired through previous experience with little or no effort, and most of the time without explicit teaching. So these terms often have the notion of theories attached to them, because they can provide explanations for different observations, and they allow us to make predictions about future outcomes, and however they lack the internal consistency and explanatory power of scientific theories, with which they are often misaligned. And I will focus now on two key phenomena that are very characteristic of why we talk about intuitive conceptions at all. So first of all, it is the phenomena that's related to the developmental trajectory, and seminal studies in which children's intuitive conceptions were studied, conducted, for instance, by Thurn and Inagaki, were focused on the developmental comparison where children's responses were compared to adult ones. And indeed, younger children would make generalizations based on their intuitive conceptions that adults would not. So, for instance, if we look at the developmental trajectory of children's understanding of what it means for something to be alive, they associate the idea of living beings with entities who have motion. And therefore, they apply this idea to other objects such as the moon, which they perceive as having motion, and therefore children judge this as an entity that is alive, whereas adults do not judge the moon as something that is alive. So they overgeneralize this idea of motion equals living to the moon, and yet also these intuitive conceptions can lead them to make certain errors on different topics. So for instance, since they associate living beings to motion, plants, since they don't perceive them as having motion, they would make errors where they would judge them as non-living entities, whereas adults do not make these errors. On the other hand, a second phenomena that is very characteristic of intuitive conceptions, it is that they are persistent. So today we have a rather rich body of knowledge that shows that adults are not totally immune to the influence of intuitive conceptions. And the empirical tasks that have been used to demonstrate this, they contrast statements that are that we call congruent statements with the intuitive conception. So statements where the scientific truth is aligned with the truthfulness that we would intuitively say. And they would contrast them with statements that we call incongruent, so where the truthfulness of the scientific theory and the intuitive theory misalign. And what we see, so through different accuracy responses and response times, is that congruent statements, adults have greater accuracy on them. They're also they have quicker response times on them, and this is observed across various scientific domains among experts and extensively studied in mathematics, which is going to be my focus very soon. So a key question that this raises in our lab and what we study is, why do these intuitive conceptions persist and interfere among adults, and how can this also, is there something in common that also explains this overgeneralization that children make in, when they start learning? And in the present study, so we want to explain this developmental pattern of children's overgeneralization and the persistence among adults through typicality effects. So in typicality effects, they find their roots in theories on concept formation and categorization. So as Eleanor Rush showed, mental categories are defined as not having strict boundaries. Instead, they evolve around prototypical exemplars, and there are most central representative examples that will be seen as prototypical of a category, whereas other members can be included in varying degrees. So such categories have graded structures, meaning that certain entities will be considered as more easily belonging to the category than others. And this is empirically tested often through either tasks where we search for representative categories and we ask participants to do typicality ratings. So for instance, we would show dogs such as, let's say, a Labrador and a Chihuahua, and we would ask participants to judge, is one of these entities more a dog than another. But there are also production tasks where we would ask participants to generate examples of a certain category, and we would look at how often a certain exemplar emerges, and we would consider this to be like the culturally shared prototype. So in the current study, the overarching questions that motivate this research is, can we treat intuitive conceptions as category prototypes? And this for us means shifting the focus from studying interference effects to studying typicality effects. And to do so, resorted to a study of arithmetic operations and word problems, because in fact, arithmetic word problems, they're very handy because we can study many phenomena through them, because they have a certain semantic context that is put into relation with also an arithmetic content, and therefore it mobilizes different sources of knowledge. And arithmetic is a field in which domain there's a large body of evidence that has documented the intuitive conceptions. And so, for instance, the intuitive conception of subtraction is seeing it as taking away, of addition is seeing addition as putting together, multiplication as repeated addition, and division as partitioning. And a particularly useful way of exploring these typicality effects with the help of word problems is by resorting to problem-posing tasks. So problem-posing tasks are often used in the literature to understand how children understand mathematical concepts, but they can also be used as a production task to study the typicality effects, which is what we do in the current study. So we aim to address these three research questions. Are problems congruent with the intuitive conception more frequently posed than others among the adult population as a demonstration of these typicality effects? But also we raise the question, will adults be able to pose incongruent problems with intuitive conceptions when we give them explicit cues to kind of search for these problems? And we also address the question, does expertise have an influence on how they perform on these previous two, in regards to these previous two questions? So to answer this, We collected data in 3 different populations, so bachelor students in educational science who come to study in this building, as well as 257 high school teachers. Among them were also mathematics teachers, and also 84 pedagogical advisors. So pedagogical advisors are a population that we consider like an expert population here. So they're pedagogical advisors in France who are actually teacher trainers and who have a certain expertise, and they're supposed to be counseling teachers about their pedagogical practices. So we put in place 2 tasks. The first one was a free problem posing task, where we would ask participants to come up with a word problem for each one of the arithmetic operations. And what we expect here, what our predictions are, is that when we ask them to produce an arithmetic problem, they would, so this aligns with the idea that what they would give as an example would be the category prototypes. And what we expect to find is that they would present problems that are congruent with the intuitive conception. And the second task afterwards, which we asked for all 4 arithmetic operations, is we gave a certain queued problem posing task where we asked them to come up with a word problem that would go against the interferences of the intuitive conception, with this prediction that ideally, if they are able to go past their intuitive conception, they would give these atypical examples, which would be problems that are incongruent with the intuitive conception. So there is a well-established body of literature that documents the different semantic categories of arithmetic word problems, which made it possible to also apply this for the coding of the collected problems that the participants posed. So for each one of the arithmetic operations, we resorted to the problem categories that could be that are aligned with the intuitive conception, and on the other hand, we coded the problems of other semantic categories of problems as problems that are incongruent with the intuitive conception. And initially 25% of the data was double coded, and then through agreement we proceeded for the rest of the data. So what this gives when we look at it more precisely, the first task we would ask participants, can you come up with a subtraction word problem that can be solved using the operation 22 minus 3? And we also had different numerical values, so 3 different counterbalanced situations with large numbers or no numbers. And okay, and so for instance, if we would see a participant who, so what we would expect, what we predict is that they would give an example such as Luke has 22 marbles, during recess he loses 3 marbles, how many marbles does Luke have now? So this is something based, that is very typical of this semantic category of taking away, or actually, well, a transformation problem with the result unknown, and this is something that would then be coded as a problem congruent with the intuitive conception. As for the second task, we would ask them, is it possible to come up with a subtraction word problem whose solution is found using a one-step subtraction, and that describes a gain? So we would give them hints about like the semantic nature of the problem that they should be producing, so kind of cue them to go against these inferences. And what we could expect as a response that would go in this direction would be if they give a problem. Joe had some marbles. Tom gave him more marbles, so he gained 3 marbles. And now he has 22 marbles. How many marbles did he have in the beginning? So this is something that belongs to the semantic category of word problems with the start unknown. And this is something that is incongruent with the intuitive conception. So looking at the results, what we see is that, first of all, overall, so for all the populations and all the word problems, there is a significant difference between, for the first task, with how many problems are produced that are congruent compared to the incongruent problems. The large majority gave word problems that are congruent with the intuitive conception. And this is the case in all of the different populations. And also this is true for all arithmetic operations. So for each one of the arithmetic operations, the large majority of the problems that were posed were problems congruent with the intuitive conception, with subtraction being a bit less prominent compared to the others, but still there's about two-thirds, more than two-thirds of participants who gave congruent problems. And when we look at the second task, so this is where it's also interesting, where we cued them to go against these inferences about stemming from intuitive conceptions. It is only about a quarter of them who actually said that it is possible to come up with such a problem and managed to give an example of a problem that goes against the intuitive conception, whereas about a third of them said that it should be possible, but that they cannot find the problem. And the rest of them either said no, either said yes, but still gave a problem that was congruent with the intuitive conception. This pattern was also replicated for each arithmetic operation. And when we look also at the different populations, so this same kind of percentage, around 20%, is observed among bachelor students and high school teachers. And when we look at the math teachers, it's still only about a third who managed to give an incongruent problem. And pedagogical advisors also, so a bit more, a bit greater part of the population gave incongruent problems, but still it only remains a third. So what we see here is, so the main key findings of the study, that the vast majority of the participants spontaneously come up with examples that are congruent with the intuitive conception. Only about a quarter of them succeed to go against the entailments of the intuitive conception when explicitly cued to do so. And a consistent pattern is observed among the different populations. And we can see that among the expert populations in our study, they have a slightly better performance, but are still largely influenced by this prototype. And so if we look at what this means in our perspective and looking how we can consider these typicality effects to explain both the developmental origin and the persistence of intuitive conceptions, how we would describe this, so it's just for illustrative purposes, what we would say is that young children, for young children, the intuitive conception, it's the only knowledge that they have about this situation. So they don't have knowledge that they need to be suppressing. So what this means is that they start off with this, and for instance, for them, subtraction at this point in learning, it is only equivalent to this idea of taking away. So also when they would encounter a problem where they need to be taking away, they can easily find a solution to it because what they are actually doing is simply using this intuitive conception. But when they are faced with an incongruent problem, such as the one that we saw, which also can be solved with the same arithmetic operation, for them it simply falls outside of the scope of this intuitive conception. It is not at all part of this category of subtraction, which is at this moment equivalent to taking away. And so they kind of encoded, they can notice maybe the encoding, but they just don't have the strategies to solve it because they cannot access this idea that they can use as subtraction. And basically, it would mean that progressively, so if we rely on the different ways conceptual development evolves, they would eventually reach this point where also these atypical situations would belong to this category of what subtraction is. And the fact that they are later at the periphery of this category would also explain as to why adults have difficulties in finding such examples even when they're cued to do so. It's simply because they're at the far spectrum of the category. So maybe I'll just take a small minute to mention that this also kind of opposes the approaches that are often solicited when we try to explain this persistence of intuitive conceptions, namely trying to justify them through these dual models and inhibition. It does point to this importance that there is this certain cognitive conflict that emerges, and that is important, but it cannot really explain both of these sides of and the developmental effects and this persistence and why it is harder to access these types of situations. So I want to thank my team and the colleagues who also contributed to the study, Lucas Reylin, who is here, and Stephanie No, who you might have seen around. And maybe I'll take a moment for any clarification questions, and we'll go on through the other talks and have maybe a greater discussion at the end. Thank you.
All right. Hello again, and thank you, Katarina, for organizing this and inviting me to participate. Katarina actually covered some of the methodological ground that I was going to cover at the beginning, but I'll still cover it just quickly. I'm going to put up some statements, and I want you to mentally categorize them as true or false as quickly as you can. Bricks have weight. Numbers have weight. Clouds have weight. Flames have weight. All right, these are the answers. True, false, true, false. Chances are you had an easy time with the first two sentences, statements, and then the second statements might have given you pause as you had to consider, do clouds really have weight? Do flames have weight? And that's because the first two statements are consistent with our intuitive theories of matter, whereas the second ones are not. So matter, from a scientific point of view, is anything composed of molecules. And so if it's composed of molecules, it has properties true of all matter, including having weight. But intuitively, we think of matter as something you can see or touch. The prototypical material entity from an intuitive perspective is a solid object. And so on that conception, clouds don't seem all that material because they float. Flames do seem somewhat material because we can perceive them, we could even touch them. But flames are just a light energy, and clouds are in fact material. So in 2012, we used this statement verification task to look at the resilience of intuitive theories across a variety of domains. If, when we learn a scientific theory, we overwrite our intuitive theory, then statements that are inconsistent with an intuitive theory should be just as easy to verify as statements that are consistent with those theories. But if they remain, then people should be slower and less accurate for the second type of statements that I had on that earlier slide. And what we found is that across 10 different domains, including matter's over there on the right, for statements that were inconsistent with intuitive theories of the domain, people were less accurate at verifying them relative to closely matched intuition consistent statements. And when you answered correctly, you verified a statement correctly, it took you longer to make your verification if the statement was inconsistent with intuitive theories of the domain relative, to, again, to those closely matched statements that were consistent with the intuitive theories. This turns out to be a robust phenomenon. Many people have replicated and extended these findings using different statements that exemplify different domains. Katarina in some way did that herself, though not a speeded verification task. So I think we can take it as established that that when you learn a scientific theory, it doesn't replace the earlier intuitive theory, but rather coexists with the intuitive theory. And so there's lingering tension between two ways of interpreting some kind of natural phenomena. And what I want to talk to you about today are some studies that looked at the malleability of that tension. Studies that looked at whether the conflict between scientific and intuitive interpretations of an idea are malleable with some contextual priming, and are they malleable with more direct targeted training. So more specifically, can participants be induced to access counterintuitive scientific ideas with greater accuracy and greater speed given priming and training? So let me first start with the priming study. Our participants in the study were 100 undergraduates, and we asked them to verify 480 statements as quickly as possible. They were making true or false judgments. And we have 4 types of statements that were like the statements that you just saw. We had intuitively true statements like bricks have weight. So that's true from a scientific point of view as well as an intuitive point of view. Intuitively false statements like numbers have weight, which is both scientifically false and intuitively false. And then we had the more interesting statements where there's a conflict. So counterintuitively true statements like clouds have weight, which is scientifically true but intuitively false. and counterintuitively false statements like flames have weight, which is scientifically false but intuitively true. All right, so participants verified a total of 480 statements. Half of those were about matter, and half of them were about life. And the way that we constructed our statements is that we took 3 predicates that are properties true of all material entities, 3 properties true of all living things, and then combined them each with 80 subjects. So here are our predicates in the domain of matter. Has weight, has a temperature, and occupies space. Anything material exhibits these properties. And then these were our properties for the domain of life: reproduces, respires, and needs nutrients. So anything alive exhibits these properties. So we took those predicates and then paired them with 80 different items, and we gathered together our items using this logic on this 2x2 table, where we considered whether science and intuition agree that the entity is part of the domain. So in terms of matter, science and intuition agree that solid objects are part of the domain. Science and intuition also agree that non-material entities like dreams, songs, and numbers are not part of the domain. So when you pair those with a predicate, they create our intuition consistent set of statements, our control items, essentially. The other diagonal illustrate entities that, when combined with the predicates, create the counterintuitive statements. So from a scientific point of view, gases are material, but intuition says that they're not. And then from an intuitive point of view, certain forms of energy seem to be material. They have certain material properties, like you can see them or even feel them, but they're not composed of matter, and thus they're not part of the domain from a scientific point of view. So we did the same thing in the domain of life to identify a total of 80 items, 20 from each of those cells that we could combine with our predicates. So that's how we constructed our assessment statements. So in terms of priming, the way participants completed the task is that they verified statements with the same predicate in a whole block. So they verified statements about whether or not something has weight altogether. And in between each statement, they saw an image. And some participants saw images that were intended to prime an intuitive sense of having weight, like an image at the top, where it's priming the sense of felt weight. And other participants saw images that were intended to prime a scientific sense of weight, like force diagrams. And you saw either one or the other. You were either in the scientific prime condition or the intuitive prime condition. We didn't mix them. So for the predicate has temperature, you can see an example intuitive prime at the top, an example scientific prime at the bottom. And for the predicate occupies space, intuitive at the top, scientific at the bottom. For the biological primes, these are primes corresponding to reproduces. So the intuitive one at the top, the scientific one at the bottom. Here are primes for respires and primes for needs nutrients. So in general, our intuitive primes showcase people doing everyday activities, and our scientific primes showcase diagrams or photographs of things that you couldn't see with the naked eye. All right, so let me show you how priming affected statement verification. So here we've got the proportion of statements correctly verified on the y-axis, and on the x-axis, it's whether you saw scientific primes, intuitive primes, or no primes. And the first thing you'll notice is that these two lines are far apart. So participants were much more accurate for intuition consistent statements than intuition inconsistent statements. The other effect I hope you'll see is that the lines move upwards. So scientific primes did lead to higher accuracy relative to no primes and intuitive primes. In fact, statistically, no primes and intuitive priming led to the same results. It wasn't that intuitive primes led to less accurate verifications. When it came to speed, though, we found no effects of priming. So we found the effect that intuition inconsistent statements were verified more slowly than intuition consistent statements, but it didn't matter whether or not you received a prime or what kind of prime you received. So this implies that participants verified counterintuitive scientific ideas like clouds have weight more accurately when primed with scientific images like force diagrams, but they didn't do so any faster. So that implies that these persistent response lags imply that intuitive ideas are elicited automatically, just with the notion of having weight, elicits the idea of felt weight, and it takes a certain amount of time to suppress that intuitive idea. So priming produced a small effect on accuracy, no effect on speed, and we thought maybe we would see greater effects and maybe effects that extended to speed as well with direct targeted training. So in the study I'll tell you about now, we had 138 undergraduates, and we involved them in a pre-post design. So at pretest, they verified 240 statements. Half of them, the statements were about life, half of them were about matter, involving all three sets of predicates that you saw before, or 6 sets when you include both domains. And then they got a tutorial, either a tutorial about the scientific properties of life or a tutorial about the scientific properties of matter, followed by some attention checks that all the participants passed. And then that was followed by a post-test, where, again, our statements were about life and matter, and they involved the same predicates, but they were new statements because we pulled statements with brand new subjects that participants hadn't seen at pretest. All right, so our tutorials did 2 things. On the one hand, they emphasize what makes something alive and what makes something material, while also refuting common misconceptions about these domains. So for instance, the misconception that plants do not move was refuted with time-lapse videos showing plants moving towards a light source as they grew. Or the misconception that gases have no weight was refuted with the demonstration that if you fill up a balloon with air and you put it on a scale with an empty balloon on the other side, the air-filled balloon will pull the scale down. All right, so the way I'll show you these data is in terms of instruction. So what I mean by that is if you are a participant who is randomly assigned to receive the life tutorial, then the instructed domain for you consists of statements about life, and the uninstructed domain consists of statements about matter. And if you randomly receive the matter tutorial, then the instructed domain consists of statements about matter, and the uninstructed domain statements about life. So first, let's look at accuracy in the uninstructed domain. So the 2 lines that correspond to the 2 types of statements are quite far apart, replicating the fact that intuition consistent statements are verified more accurately than intuition inconsistent statements. You'll also see that the lines are moving upward, just indicating that participants, as they became more familiar with the task, more comfortable with the task, they responded more accurately from pre-test to post-test. But the gap between the 2 types of statements did not close. So we didn't see any effect of learning, and we shouldn't have because this was the uninstructed domain. In the instructed domain, you see all the effects I just mentioned, as well as an interaction between the type of statement and the assessment period. So that gap between the 2 types of statements is closing from pre-test to post-test as participants are responding to the counterintuitive statements more accurately. When it comes to speed, first we'll look at the uninstructed domain. We replicate that gap between the 2 types of statements, where participants are verifying intuition inconsistent statements more slowly than intuition consistent statements. That was true at pretest and at posttest, even though participants got faster for both types of statements at posttest as they became more comfortable with the task. But the gap between the 2 types of statements is the same. And again, it should be the same because this is the uninstructed domain. The real question was, in the instructed domain, could we reduce that gap? And we could not. So the gap was consistent from pre-test to post-test. So what we found is that similar to priming, with training, we increased participants' accuracy at verifying counterintuitive scientific ideas. relative to closely matched intuitive ones, but we did not increase the speed with which they did so. And these effects were consistent across domains and across predicates. I didn't show you those data. I don't have time to do that. But if I break it down by life versus matter, or even more finely by has weight versus occupy space, et cetera, you see consistent effects across the board. All right, so to conclude, counterintuitive scientific ideas can be verified more accurately given the right context or the right kinds of instruction. But response lags persist, implying that when you come across a statement about some natural phenomenon, the intuitive ideas are elicited automatically and require some amount of time to be suppressed in order to privilege the correct interpretation. I think these data have some educational implications. Perhaps scientific ideas can be accessed more readily and indeed learned more readily in environments that privilege scientific cues over intuitive ones. And that could happen with instructors who are aware of this conflict between intuitive and scientific interpretations of terminology, and help students privilege the scientific interpretations over the intuitive ones in whatever ways are useful in that class. But something I want to point out is that even though we found effects of priming and training on accuracy, they're very small relative to the effect of statement type, whether or not a statement was consistent with intuition or inconsistent. So let me just show you some effect sizes. So here's an odds ratio. So the odds of answering a statement accurately, if primed scientifically, was 1.57. The odds ratio for answering a statement correctly if trained on that type of material, given content-specific training related to that statement, was 1.69. And the odds of answering a statement correctly if it was consistent with intuition versus inconsistent with intuition was 6.3. So a much stronger effect of statement type. So I think that these effects, even though they demonstrate that there's some malleability here in the tension between scientific and intuitive interpretations of natural phenomena, they also demonstrate the robust resilience of intuitive theories. All right, so let me acknowledge my funding sources: the James S. McDonald Foundation, the National Science Foundation, my collaborator on this work, Andrew Young, former postdoc professor at Northeastern Illinois University now, and the team of undergraduate researchers who assisted with this project. And these are actually old data, but they were just published last year in Cognition if you're interested in accessing them. All right, so I will open the floor to one clarification question, I guess.